WebLLM, a high-performance in-browser LLM inference engine. Charlie F1, Yucheng Qin, Zhen Zhao, Ruhong Lai, Hongyi Jin, Yixin Dong, Bohan Hao, Mengxian Yu, Yiyan Zai, Sudeep Agarwal, Hongrui Gao, Siyun Feng, Tianqi Chen, Carnegie Mellon University, Shanghai Jiao Tong University, NVIDIA. Abstract. Advancements in large language models, LLMs, have unlocked remarkable capabilities. While deploying these models typically requires server-grade GPUs and cloud-based inference, the recent emergence of smaller open-source models and increasingly powerful consumer devices have made on-device deployment practical. The web browser as a platform for on-device deployment is universally accessible, provides a natural agentic environment, and conveniently abstracts out the different backends from diverse device vendors. To address this opportunity, we introduce WebLLM, an open-source JavaScript framework that enables high-performance LLM inference entirely within web browsers. WebLLM provides an OpenAI-style API for seamless integration into web applications and leverages WebGPU for efficient local GPU acceleration and WebAssembly for performant CPU computation. With machine learning compilers, MLC LLM, and Apache TVM, WebLLM leverages optimized WebGPU kernels, overcoming the absence of performant WebGPU kernel libraries. Evaluations show that WebLLM can retain up to 80% native performance on the same device, with room to further close the gap. WebLLM paves the way for universally accessible, privacy-preserving, personalized, and locally powered LLM applications in web browsers. The code is available at the GitHub link. Introduction. Recent advancements in large language models, LLMs, have unlocked remarkable capabilities, such as question answering, code generation, and even reasoning. As the most capable models require server-grade GPUs, the models are typically hosted on the cloud during inference. However, open source providers recently started releasing smaller models around 1 to 3 billion parameters that achieve competitive performance. Meanwhile, consumer devices have grown increasingly powerful. A 4-bit quantized 3 billion model decodes 90 tokens per second on an Apple M3 laptop. These trends make on-device LLM deployment both promising and practical. On-device deployment preserves privacy, enables personalization with local data, and unlocks new paradigms such as hybrid inference where cloud-based and on-device deployments coexist. The web browser is an appealing platform for on-device deployment for 3 reasons. First, the browser is a natural agentic environment for tasks like managing calendars, responding to emails, and creating documents, activities that could potentially be automated by browser-based agents. Second, the web browser is universally accessible. Users only need to open a URL without installing any additional software. Third, the browser abstracts away the complexities of different device backends. Although mobile devices come from various vendors, browser-based technologies such as WebGPU are backend agnostic. For instance, instead of implementing GPU kernels for each backend, for every new LLM operator, developers only need to provide a single implementation in WebGPU. To address these opportunities, we introduce WebLLM, a high-performance in-browser LLM inference engine. This open-source JavaScript framework deploys LLMs locally in the browser, empowering web developers to integrate LLM capabilities into their web applications. WebLLM offers an OpenAI-style API for easy integration, leverages WebGPU and machine learning compilers for efficient local GPU acceleration, uses WebAssembly for performant CPU computation, and supports web workers to separate the backend execution to prevent any disruption to the UI flow. Our evaluation demonstrates that WebLLM can maintain up to 80% native performance, with a potential to further close the gap. System architecture and key components. WebLLM is a JavaScript framework that deploys LLMs locally in the client-side browser, enabling LLM-based features in web applications. Achieving this goal poses three challenges. WebLLM needs 1. A standardized API that web applications can easily incorporate. 2. Adaptation to the browser's runtime environment. And 3. Efficient GPU acceleration. As shown in Figure 1, WebLLM's architecture addresses these challenges by dividing the system into three parts correspondingly: a user facing engine, service worker MLC engine with endpoint like behavior, an encapsulated MLC engine that resides in the web worker, a background thread in JavaScript, and ahead of time compiled efficient WebGPU kernels. An LLM inference engine. Web developers instantiate a lightweight service worker MLC engine in the web application frontend and treats it like an endpoint. The engine loads an LLM when specified, takes in an OpenAI-style request at any time, and streams back the output in an OpenAI-style response, which the web application can use to update the front end. This familiar endpoint-like design brings several benefits. Endpoint-like APIs are JSON in, JSON out, and thus have well-defined behavior. Besides, OpenAI-style API is widely adopted and it makes WebLLM easy to integrate into existing projects. This design also allows WebLLM to extend to advanced features with minimal changes to the API. Advanced features that WebLLM supports with this API include structured generation with JSON schema and context-free grammar, image input with vision language models, and loading multiple models in the same engine for applications like retrieval augmented generation. Adapting to the browser runtime. Unlike most LLM inference engines that are either C++ or Python based, WebLLM is implemented in JavaScript. This non-conventional LLM runtime environment requires WebLLM to adapt to the technologies offered in browsers to ensure high performance. Web workers. LLM workloads are computationally heavy and could block the UI if run on the main thread. In JavaScript, web workers are used to separate heavy computation into background threads for a smooth UI. Therefore, WebLLM leverages web workers by having two engines: a lightweight front-end engine, service worker MLC engine that is exposed to the web application, and a back-end engine, MLC engine, and the worker thread that actually computes the LLM workload. The two engines communicate via message passing, and the messages are simply OpenAI requests and responses. WebGPU. LLM inference requires GPU acceleration. WebGPU is a JavaScript API that allows web applications to leverage the device's GPU in the browser. WebGPU is also backend agnostic. The same WebGPU kernel can run on devices with different GPU vendors, such as Apple laptops with M chips and laptops with NVIDIA GPUs. Therefore, WebLLM leverages WebGPU for any workload in LLM inference that requires GPU. We discuss in detail how such kernels are generated in 2.3. WebAssembly. Having WebGPU is not enough, as LLM inference also requires non-trivial computation on the CPU. WebAssembly, WASM, is a portable, low-level bytecode that can be compiled from C++ code and run in JavaScript runtime with near-native performance. Therefore, instead of re-implementing CPU workload in JavaScript, WebLLM leverages mscripting to compile high-performance subsystems written in C++ into WebAssembly for various CPU workloads in LLM inference, including a grammar engine for structured generation, sequence management in the paged KV cache, and tensor manipulation for launching kernels. This enables C++ code reuse for WebLLM without sacrificing performance. GPU acceleration with WebGPU via MLC LLM. GPU acceleration is crucial for high performance LLM inference. WebGPU provides a standardized API to leverage GPU and JavaScript and abstracts out devices with different GPU vendors. However, unlike native backends such as CUDA, WebGPU does not have accelerated GPU libraries for common kernels. This makes it challenging to write high performance customized GPU kernels such as paged attention and flashed attention for WebGPU. WebLLM resolves this by leveraging machine learning compilation libraries, MLC LLM, and Apache TVM to compile performant WebGPU kernels. MLC LLM takes in any open source model's implementation in Python, which uses techniques such as the aforementioned paged attention and flash attention, and compiles the model's computation into the backend of interest, in this case, WebGPU. Besides compiling to the specific target, MLC LLM also provides both graph level optimizations, for example, kernel fusion, and operator level optimizations, like gem tiling, to ensure the kernel performance. MLC LLM converts open source models into two artifacts: converted weights and a WASM library. The WASM library contains both the WebGPU kernels and non-kernel functions in WebAssembly. As shown in Figure 1, the models that WebLLM loads in are compiled ahead of time and hosted online. Evaluation. We evaluate the performance of WebLLM by comparing its performance with MLC LLM on the same Apple MacBook Pro M3 Max. The former leverages WebGPU kernels and a combination of JavaScript and WebAssembly runtime. The latter leverages Metal kernels and a combination of Python and C++ runtime. Our results show that WebLLM preserves up to 80% of the decoding speed of MLC LLM. There are various opportunities to further close the gap, including leveraging recent WebGPU features such as shuffling and a more careful optimization of WebLLM's runtime in general. Conclusion. WebLLM demonstrates that high-performance on-device LLM inference is feasible directly within the browser. As an open-source JavaScript framework, it empowers developers to integrate advanced LLM capabilities into web applications without sacrificing privacy or requiring server-level resources. WebLLM thus paves the way for accessible, personalized, and private LLM-driven experiences in everyday web usage. My summary. This paper presents WebLLM, an open source JavaScript framework for running large language models directly in web browsers. By leveraging WebGPU for GPU acceleration and WebAssembly for CPU based tasks, WebLLM achieves up to 80% of native performance on the same device. It provides a familiar OpenAI-style API, allowing developers to easily integrate on device LLM features into web applications. This approach promotes privacy, personalization, and universal accessibility, enabling powerful language model capabilities without requiring server-side resources.